we're continuing with Unit 1. Now we're in Section 1B, which is compound interest. And there's a 1C section for annuities, so that's the next thing we're going to go to. And today, I just wanted to build on 9.2 a little bit further. And if we built on a little bit further, what we're talking about here is calculating the present value. Now, okay, you say, well, what's the difference? Future value is looking into the future. Present value is the reverse of that. You're given an amount in the future that it's going to grow to. Say, for example, something's going to grow $10,000 in the future. And given a rate of interest and given the amount of time, you want to know how much is it worth today? So what we're doing is working backwards in terms of time with the present value. So this is what I wanted to look at today. Now, if you only learned this formula right here, let's say, for example, let's go back. I got to hop back here. If you only learned the future value formula and you said to me, well, I don't know what the present value formula is. Well, the present value formula is exactly the same formula, but rejigged to put PV on that side of the equal sign, okay? So PV would equal FV divided 1 plus I to the n. So as we go to look at 9.3, we're going to use the same formula, but rejigged to put present value on the left side of the equal sign. So present value of a single sum of money is the amount that, if invested on a given date at a specific rate of interest, will equate to the sum of the amount invested in the compound interest earned on its investment with a face value of the future single sum of money. I wish I didn't put that there. That's a big fancy way of saying, you know what the value is in the future? You want to calculate what is the value now, given the length of time and given the interest rate. So this is the same formula rejigged. So the future value over 1 plus I to the n. And I, again, periodic interest rate, n is the total number of compounds in the whole event. So here we have an example. Again, it's a reverse example of the one I've given you before. So you assume that you need to invest enough now so that you'll have $100 at the end of the year, assuming that the stuff is compounded quarterly, 4 times a year, for 1 year. And the nominal interest rate is 8%. How much will you need to invest now in order to have $100 at the end of the fourth quarter? So here we got our timeline, which is so important. I can't overstress the value of drawing a timeline. So we're looking for how much do I have to put in now if I am going to get $100 at the end, okay? So what we need to be able to do is to do a little bit of math on it. So we know that there are 4 compounding periods. So, and it's only 1 year. 4 times 1 is 4. We know that the nominal interest rate is 8, and interest rate is always given in a annual format, provided that it doesn't say otherwise. So what we need to do is take the 8 and divide it by the 4 periods here, the 4 compounding periods, to get 2% per period. We put that in the formula. So the future value is 100 divided by 1 plus the 2%, which is the n, which is 0.02, to the power of the total number of compounds, to the power of 4. And this then comes to $92.36. Now, here's something you need to remember, and this is something that I wish I had realized. Yeah, maybe I was just thick when I did this first, okay? If I had drawn the time, I didn't draw timelines when I learned this first, and I said to myself, this is harder. And look, it's not. If I had drawn a timeline, logically, you're going to think money grows as time goes by, right? So here, whenever we have a problem like this, we're looking for a smaller amount on the left-hand side, basically now, than we had at the end, because money is going to grow. So in order to self-check yourself to make sure you got it done right, you have to ask yourself, whenever I'm calculating a present value, is the number smaller than the value at the end, which is the future value. Is the number smaller? And if it is, you probably got it done right. So it's a little bit of a mental check to kind of always think about, am I doing this correctly? Got some examples in here. And again, the samples are very, very similar to what we saw in the last one. So example 3 says, if an investment can return 4% compounded monthly, so we know that it's 12 compounds a year if it's monthly, what amount must you invest now in order to accumulate $10,000 after 3.5 years? So here we know that the future value is $10,000. We know the rate is 4% compounded monthly. So we got to take 4% divided by 12 in order to calculate the periodic rate. And 3.5 years. Now, we're dealing with months here. So we really need to think of, okay, how many months is that? It's compounded monthly. So 3.5 years times 12, right, will give us 42. So that will be 42 months. Again, common terms. If we plug that into the formula, the present value then is the future value, $10,000. And you'll notice here, and I just want to clarify this too. Notice this formula is saying if v bracket 1 plus I to the minus n. That's the same exact thing. That formula to the minus n, if you were to exponent to the minus n, that's exactly the same as doing this, taking the f value and dividing it by 1 plus I to the n. So either one of those formulas, these formulas are the same, just mathematically they're different, okay? But they do exactly the same thing. It will yield the same answer. So in this case, 10,000, and I would say divide it by 1 plus I, which would give us this number right here, to the power of 42. So that would be this type of formula right here. Or we could easily say 10,000, 1.033 to the minus 42. It will give you the exact same answer. The point is that I want to make sure is that you're saying, look, the money value that came out of that, or the present value, is smaller than the end amount. The end amount was 10,000. It's smaller. So odds are it's done right. So effectively, we need to invest about $8,700. And that would have to sit there for 3.5 years in order to grow to around 10,000. Okay? Round numbers. Mr. and Mrs. Nugent's property taxes amount to $3,450. They're due on July 1st. What amount should the city accept if the taxes are paid 8 months in advance and the city can earn 3.6 compounded monthly on surplus funds? Okay. So in this particular instance, the $3,450 is the amount on July 1st. Then we want to think, well, what is the present value 8 months before that? Let's look at the present value 8 months before that. So let's look at that. The future value is $3,450. The interest rate is 3.6%. We need to convert that to the periodic rate. So 3.6 divided by 12 will give us the periodic rate of 0.3% per month. We plug that into the formula, and that's 3,450 divided by 1.03 to the power of 8, or 3,450 times 1.03 to the power of minus 8. And that will come to 3368.31. So the city, 8 months before, the city would accept 3368.31 to be equivalent to 3,450 in 8 months' time. So I think that should be a pretty straightforward one, a typical type of problem. Another typical type of problem that we have two payments of $10,000. What we're doing here is comparing, what we're looking at two separate payments with some sort of a interest rate change between them. And again, almost identical to the type of problem we've seen in the last section when we were calculating the future value. So we got two payments of $10,000 each, must be made 1 year and 4 years from now. If money can earn 3% compounded monthly, what single payment 2 years from now will be the equivalent to the two scheduled payments? Well, okay. So we've got our timeline drawn. You see the timeline right here. Okay. The timeline then shows the 1 year mark when there's $10,000 paid. And it shows the 4 year mark when there's $10,000 paid. That's what it says in the problem. Two payments, 10,000, 1 and 4, year 1 and year 4. So there's that. And then it says what single payment 2 years from now. So we need a 2 year mark. So this 2 year mark, which is really what we call the focal point. This is what we're trying to calculate. What's the value in 2 years from now? If you draw this timeline, it makes this so clear, or so much clearer. So we take the 10,000 in year 1. We got to bring it ahead to year 2. So what we need to do is to get the future value of that. We're saying what's 10,000 worth in a year's time, basically. That's what we're saying here. And the 4 year payment, we want to bring that back to 2 years. So we got to bring it back 2 years. And we're asking ourselves, how much is that worth in terms of the present value? Okay, so we're calculating a future value and we're calculating a present value. So it's effectively two of them. So we need to calculate the future value. We're bringing ahead 12 months. Seeing in order to get common terms is a monthly compound, so we need to deal with monthlies. And so we just plug the numbers into the formula and you'll get 10,304. So basically it takes that 10,000, brings it up here. And as time goes by, you know the money is going to go higher. So 10,304. This one here, we're going backwards in time. So this is going to be a smaller amount. So we're going to take the 10,000. It's 2 years. And the interest rate is the 3% compounded monthly, which works out to 0.25%, which is 0.0025 in the decimal, and to the 24. So if we use the formula this way, the present value formula this way, meaning that we do the negative number. Otherwise, we can do 10,000 divided by 1.025 to the power of 24. This will come to 9,418. So effectively, this one here is worth 9,418. This one here is worth 10,304. We simply add the two together, PV and FV, and that will give you the total value of the investment at year 2. That would be equivalent to. So we've done both. Again, the hardest part in any of these problems is this number line. The mechanics of this should be pretty straightforward. It's tedious, but the mechanics of it should be pretty straightforward. And we also got this issue of economic equivalence. So if we think about equivalency, show why the receipt of the payment in example 8C should, the recipient of the payment should be indifferent between the received values, okay? So in this particular instance, if the recipient ends up with the same economic position with either alternative, you'd be indifferent. That's what that means. They're both worth the same. So we can calculate how much money the recipient will have 4 years from now with each alternative, assuming that any amounts received are invested at 3% compounded monthly. So right here, the two alternatives are presented. So the first alternative was saying, okay, we've got $10,000 and that was the first year. We got $10,000 put in the 4th year. Let's find out the value of it at the end. So we're just bringing it up here. That's effectively what we're doing here. And in the other instant, in the previous problem, we know that we calculated the value at year 2 to be 19,722.51. This was calculated back here, right? So if we bring that ahead 2 years, two of these should be the same. And in fact, we can prove it. So in this particular instance, in the first instance, we've done the future value of this 10,000. Okay, using this formula, there's all the churning that went in there. And the 10,000 at year 4, we don't need to do any work on it because it is 10,000 at year 4. So what we're doing is figuring out the value of this one here, bringing it ahead to year 4, adding two of them together, and that comes to 20,940.51. In the second instance, we're saying, okay, that in the 2-year mark, that was, we calculated to be 19,722.51. We're going to bring it ahead 2 years now, assuming the same interest rate and the 2-year period. Do the math on that, and that comes to 20,940.51. So we can prove that they're both the same. Any questions on those? Any questions? Questions? Checking now to see if I got any questions. No? Okay, good. So this last one here, example E, 3 payments of $1,500 each, plus a different final payment of $856.35 were made on a loan at 1-year intervals after the date of the loan. The interest on the loan is 3%, compounded quarterly. What was the original amount of the loan? So again, we've got some timelines on the go here. 3 payments of $1,500 each, first of all. And they were made at the end of the year. So we need to be able to say, okay, let's think about how much $1,500 bring it back 1 year. Another $1,500 bring it back 2 years. Another $1,500 bring it back 3 years. And in the 4th year, it was $856.35, bring that back 4 years. So we need to be able to look at each one of them. So this is a summary of what was happening here. So in this particular instance, then, the interest rate, what was the interest rate here? 3%, okay? 3% compounded quarterly. We take 3, divide it by 4. That will give us 0.75%. So that's where that comes from. The N is the number of total. So in the first year, we know that it's compounded quarterly. 1 year, 1 times 4 is 4. The next was 2 years worth of, if we look at the timeline, this is year 1, year 2. There was another $1,500. Let's bring it back 2 years. Well, that's a total of 8 quarters. The third payment was 3 years, so that's a total of 12 quarters. And the final payment was in 4 years, which is 16 months, and that was $856. So all we really need to do is we got to find the present value of, in the first instance, that $1,500 brought back 1 year, and it comes to $1,455.83. The second $1,500 gets brought back 2 years, and it comes to $1,412.96. The third $1,500 payment is brought back 3 years, and it comes to $1,371.36. And the last payment is brought back 4 years to find out what the value of it was now. And so we do that, and that comes to $759. We add them all up, and the total comes to $5,000. In other words, that's the amount that was originally invested. That's what this was trying to pay off, effectively, this loan.